Now we're going to start looking at using the motif maker in ProMOL. Before we start making motifs, we should probably talk about what we're calling a motif. For our purposes in using ProMOL, we define a motif as a set of 3 to 5 amino acids that are found in the catalytic site of a protein. So the example you can see here is actually from a serine protease, and so on the left we have an aspartate residue, and in the middle is a histidine residue, and on the right-hand side we have a serine residue. Today you're going to learn how to use Motif Maker to create a motif for alignment studies, how to test that motif against itself to make sure it works, how to test it against homologs to make sure that it finds things it should find, and how to test it against random structures to make sure it does not find things that it should not find. We begin to make motifs by looking at the Catalytic Site Atlas. This is the website for the Catalytic Site Atlas, which is part of EMBL-EBI, the European Bioinformatics Institute. You can find the catalytic site for PDB entries. If such a site has been assigned and cataloged in the Catalytic Site Atlas, you can find it here. So we're going to look at 1T8L. So you just enter it in this box, and then hit the Search CSA button. And when we do that, we come to the page for 1T8L. Let me show you a few features of this page. On this page, it lists, first of all, the EC name or EC number for this class. There are links out to a number of other resources for EC number, for UniProt, for CSA entries with the same EC number. We'll come back to that in a little while. And entries on different resources like PDB Europe, PDB SOM, or MACI. There's also an image of the active site residues for this particular structure, 1T8L. If we scroll down a little further, we get to the part we really need for using the motif maker. This is a list of the residues by residue type. So we have the 3-letter abbreviation here for aspartate, serine, histidine, and glycine. The chain that they're all on the A chain in this case. The residue number according to the PDB. These are the numbers we'll use in Motif Maker. It also lists the residue number in UniProt, and sometimes they're the same and sometimes they're different. So these are the residues we're going to use to construct the active site in the Motif Maker. Now that we know the residues that make up the motif, we can return to PyMOL and ProMOL and go to the Motif Maker tab. Let's review all the boxes on the tab. I should mention I've populated the boxes already. Sometimes ProMOL delays, especially when another intensive program is running and the recording program for preparing these videos uses up a lot of memory. So the first box in the upper left-hand corner is the PDB box. That's where you enter the PDB ID. In this case, it's 1T8L. It's actually a chymotrypsin. The next box is the EC number. 3.4.21.1 is the EC number for chymotrypsin. I should mention, the PDB box, it's really essential to have this in there. The Motif Maker won't create a motif without it. And that's because ProMOL actually goes to the PDB, pulls the 1T8L structure file out and uses it to identify these residues, their positions, and their relative distances. The third box is the tolerance. The tolerance is the distance that ProMOL allows when it's looking for matches between a query and the motif you've created. The default value here is 2 angstroms. If you increase the number higher than that, then ProMOL will identify more things as a match, but you can also get false positives that way. We're going to leave it at 2 for right now. Next, we enter the residues. Notice that we have, on the left-hand side here, we have radio buttons. If you want to change the order of the residues for some reason, and you can do that, then you can click these buttons and then check to move up or move down. So our first residue, this is the residue box. You enter a 3-letter abbreviation for the amino acid. It can be uppercase or lowercase. Here it's HIS for histidine, chain A, residue number 57, and the backbone is off. We'll actually use the backbone in a few minutes, so you'll see where that comes in. The second residue is aspartate, or ASP, chain A, residue 102. Now my preference is to actually enter the residues in the order in which they appear in the structure, in the primary sequence of the protein. That's not necessary. I just tend to do it that way. And then if the motif isn't being as accurate or effective as I want. Sometimes I'll change the order. The third residue is a glycine, chain A, position 193. Notice that I've turned the backbone on for glycine here. The reason for that is that most structures in the PDB don't contain hydrogen atoms. And so a glycine in this structure actually is just the backbone. And in fact, most of the time when glycine is involved in a catalytic site, it's the backbone that's participating there. So we always turn the backbone on for glycine. And then the fourth residue is serine, chain A, residue 195. So once we have all of that information entered, we're going to go in and actually test. Oh, I should say, the next thing we do is to save the motif by clipping on the Save box. And it'll be saved as a user motif. And if you actually identify the file or locate the file in your program on your computer, then user motifs start with the letter U. So now we're going to test the program or test the motif against itself. So we're going to ask, does 1T8L find these residues in its own structure? So ProMOL ran the test and displayed the results in the PyMOL visualization window. I'm going to go in here and first I'm going to hide the cartoon so we can see the residues more clearly. Now I'm going to move the residues into the middle of the screen, and finally I'm going to change the display to zoom in a bit. So I'm going to zoom to an 8 angstrom sphere. And I've just discovered today that when you do that, sometimes a couple of the windows disappear. I'm not sure why that happens, but they're back now. So if we look at this, if I click on this residue, then you look up in this window, you can see it says you clicked /1T8L //C/his 57/CG. So this is histidine 57 on chain C, and it's the gamma carbon. That's aspartate 102, so we found aspartate 102 as well. This residue is glycine 193. And finally, serine 195. So it found the 4 residues it was supposed to find. But also notice that it found this residue, glycine 196, and another glycine, glycine 43. A little bit about the way ProMOL works. ProMOL looks for the residues that make up a motif to see if they're within a certain distance of the other residues. And if you look at this, you'll notice that the glycine here that's part of the motif, glycine 193, is actually a little bit distant from serine 195. And this glycine, glycine 43, and glycine 196 are both closer to serine 195 than glycine 193. Well, ideally, we don't want ProMOL to find the wrong residues in the motif. So we're going to modify the motif a little bit. The first thing we're going to do is I'm going to turn on the backbone. For the other 3 residues, and sometimes when you click on the on-off button, it flickers a little bit. So now I've got those 3 residues that are all back. The backbones are also included. Now what this means is when ProMOL does the search, it includes not only the side chain atoms, it also includes the backbone atoms to see the distances between the backbone atoms for the different residues. Now let's see if that improves the performance. So I'm testing again. It's doing the alignment, and let's see what we get this time. Even without zooming in, I can see that I still got those 2 additional glycine residues that I don't want to have in the motif. So another thing that we can do is we can change the tolerance. If we decrease the tolerance, that'll make the search tighter. So I just did that, testing it again. And again, hide the cartoon. At a tolerance of 1.5, we're still picking up those 2 extra glycines. So let's take the tolerance down to 1 and see what happens. And when we do that, we see that we just have those 4 residues that we want in the motif. Here we have histidine 57, aspartate 102, glycine 193, serine 195. Now, when you decrease the tolerance that much, there's a risk that the motif won't find motifs that are really exist in other structures. And so we try to have that tolerance as high as possible, but still only find the desired residues. So if I put it up at the 1.25 and test it, okay, that still only found the 4 residues we want. Let's try raising it to 1.4 and see how that works. And at 1.4, we're getting only the 4 residues that we want. So at 1.5, we get the extra residue, so I'm going to save it right there. Now, I've saved this motif before, so when I hit the Save button here, it warns me I've already made a user motif. Well, I'm going to save over that one. So the motif has now been saved. Now we know that the motif will find itself. Next, we want to test it on some homologs. Well, I'm going to bring the Catalytic Site Atlas screen back. And if we look, this is the Catalytic Site Atlas entry for 1T8L. And if I go onto their page, there's one of the lines on this table that says CSA entries with EC number. And so I'm just going to click on that. And it brings up a list of other entries with an EC number of 3.4.21.1. Now I may find that ProMOL works well with these or doesn't. So I'm actually going to tuck this in the lower corner of the screen here so I can see those different structures. Bring the ProMOL and PyMOL windows forward. We can still see the list of homologs here in the lower right-hand corner. And I'm just going to go into the homolog box. I'm going to enter 1ACB and test it. And when I do that, hide the cartoon. And what do we find here? We find histidine 57, aspartate 102, serine 195, and glycine 193. And I should reinforce, I'm used to doing this, I've done it a lot. But if you look up in the graphical user interface window, it lists all the residues you click on. So this is a way that you confirm that you found the residues you want. So it worked with that homolog. Well, let's try it with a couple more homologs. We'll take 1GL1. And in the case of 1GL1, it didn't find it. So just for interest's sake, I'm going to try to test it with a higher tolerance and see what happens then. And if I do that, bring one of those active sites into the center of the screen. I'm going to zoom in a little bit here. I'm going to bring the rest of PyMOL and ProMOL back. If we click on this, here's our histidine, aspartate, here's our serine, there's the glycine we want, but it picked up 2 extra glycines. So if I were working with this some more, I would probably go in and fiddle with the tolerance some. I'm not going to do that right now, but you can see that ProMOL doesn't work perfectly all the time. It still got the active site residues we want, but it found 2 extra residues. Those 2 extra glycines, which are typically problematic with these serine hydrolase motifs. And notice there are some here, 1T8L, 1T8M, 1T8N, 1T8O. Those were probably all created at about the same time by the same group. So I'm not going to do the other ones in that list. I'll try 2JET. And in this case, we see that the motif finds those 4. Oh, it found an extra residue. It found the glycine 43 that we don't want. And interesting, it didn't find the serine. Hopefully what you can see from what I've shown you is that you can create a motif and test it against its homologs, and the results, these are typical results. We get some cases where the motif works perfectly, other cases where it doesn't. And it all depends on the relative positions of those amino acids in the structure of a protein. So one of the ways we describe homolog testing is to say we're looking for true positives. So does it find the things it's supposed to find? And in fact, if it doesn't find all of the residues it's supposed to find, we would call it a false negative. Then the next thing we test for when we create a motif is we just test random structures. And so a random structure, unless it just happens to be a serine hydrolase, shouldn't be a positive match. So I just hit the test button for a random structure, and ProMOL loaded 3ZNO. If I hide the cartoon, you can see there's no catalytic site there. We'll test a couple more random structures. And so what we're looking for here are what we call false positives. A false positive is a case where ProMOL finds what it thinks is a homolog when in fact it's not. A true negative is a case where it doesn't find a match and it shouldn't find a match. So here's another case. Hide the cartoon, there's nothing there. And I'm going to test one more random structure. Takes it a minute to load the structure, and then it tests it. And if I hide that cartoon, you can see there's no active site. And what I'm going to do is I'm going to bring up the PDB site so we can look at 3K0R to see exactly what it is. Okay, so 3K0R is a Cypame mutant. If we look at it, the EC number is 5.2.1.8. It's not a homolog because it's not from the same EC class. And so we wouldn't expect it to match, to align with chymotrypsin. So this is a true negative, which is what we're looking for when we're testing with motif creation. Now once we've created a motif, we can then go over into Motif Finder. And if I go back to the Catalytic Site Atlas page and looking for homologs for 3.4.21.1, here's that list again. So I can actually place, let's do a few of these, 1 CGI, 1 CGJ, 1 DLK, 1 EQ9, 1 T7C, 1 P2N. Okay, so there's 6 structures, and I'm going to start it. I'm going to tell it that I only want to run user motifs, which are the ones I created, and I want them to be from class 3.4.21.1. And in fact, it's just going to compare against that motif that I created. While it's doing this alignment, it actually hides the visualization window. That saves computing power. And you can see that the top bar indicates completion of an individual alignment, and the bottom bar indicates completion of all of the alignments. So when we do all of these, what we see is if I go for 1 CGI and I click on 1 T8L, I'm actually going to click the Show Alignment button there. And you get a very nice alignment between the structure in red, which is 1 CGI, the query, and the structure in white, which is 1 T8L. Now, we got 4 residues to align, but we got 1 extra glycine. Notice in the results window, I guess I've created some other motifs from class 3.4.21.1. We go to 1 CGJ, double click on that, and in this case we see exactly the same result as we did just a moment ago. 1 DLK, we get an alignment there. And in the case of 1 DLK, we actually have only the 4 residues that were supposed to be found, and we get a very nice superposition of those different residues. 1 EQ9 didn't give any results. If we go to 1 T7C, and look at the 1T8L results, we see that in fact it found all 4 residues again. And so the white once again is the motif, the red is the query. And the alignment for 1P2N again includes all 4 of the desired residues. And in fact, when we get a properly tuned motif, we can run lots and lots of structures against it. In the case of the serine proteases, the results are generally pretty good. So in this tutorial, I've shown you how to create a motif, where to find your data, which is on the Catalytic Site Atlas in the Protein Data Bank, how to test that motif against itself, against homologs, and against random structures. The homologs we test to look for true positives and false negatives. The random structures we use to test for true negatives and false positives. And then finally showed you how to go to Motif Finder and selectively test only the user motifs you've been creating. And so we bring this tutorial to an end.